Hi folks, Mr. Ackerman here. Thanks for watching. Today's lesson is about lesson 8 in our homework schedule. The topic is all about sound. We're going to talk about the production of sound, how we hear sound, and also a little bit about the speed of sound. So it's a smorgasbord of ideas, and I'm going to try to go through each of them fairly quickly because they really don't need to take too much time. The section in your homework schedule would be lesson 8. Here are the sections in the textbook, 7, 1, 2, and 3. Expecting you to take some notes on those and look at sample problems. Here's a bunch of homework questions for you to try. We'll do a number of demonstrations and watch some videos in class that relate to this, and afterwards you can try some of these. We are going to do a lab that deals with measuring the speed of sound, which I think you'll find interesting, and more on that in class. There may be some hand-in for that lab, so keep your ears tuned, and make sure you know what exactly is required of you. In the learning goals, I'll ask you to read down these. You now have this as a handout that I've emailed to all of you, so in an effort to save time, we'll just skip over that for now. You can read those at your leisure. All right, so here we go. Let's get started. In section 7.1 here, they are talking to you about how sound is produced. So this is section 7.1 of the book. And if you're interested in how sound is produced, let's say from a speaker, you can read how that works. I think you'll find it quite interesting. What I'd like to focus on is the physics of the actual sound that gets produced. For example, here are some images that you'll find in your textbook. Our textbook is Physics 11 by Addison Wesley. I've just borrowed them from them to help illustrate the ideas. But for example, they show you what is meant by a wave that is low-pitched, so this is a low-sounding bass note, maybe out of a bass guitar, and what does a wave that is high-pitched, for example, out of a flute, look like? And as you can see, one of the things is that the distance between the crests is very long for a low pitch. That would be a low-frequency wave, and of course, as we know, if the frequency is low, then the wavelength is large, small f, large lambda. And of course, for a high-pitched wave, here the distances between the crests and troughs is very small, the frequency is high, frequency very high, and the wavelength very short. And I think most of you knew that already, which is why I'm going through this fairly quickly. We have mentioned this a number of times in class, and you've looked at waves on the oscilloscope, which shows the higher pitched waves to look more like this. In the diagram, they also talk about what a soft or a quiet note might look like versus a louder note. And here you can see that it's the amplitude that is different. The amplitude going up or going down from the equilibrium position to a trough or up to a crest is larger in a loud note than it is in a quiet note. So loudness is an amplitude idea, whereas pitch is a frequency or wavelength idea. And once again, I think you knew these, which is why I'm going through it fairly quickly. Here's a new idea, and this anyone who's a musician will know about this. It's the concept of octaves. If you remember back to music class, when the teacher said, play a low C, for example, and then play a high C, what did your music teacher mean? Well, he or she was saying to play a lower octave note versus a higher octave note. And when we're talking about octaves, we're talking about notes that sound the same, but one is higher than the other. So I'm a terrible singer, but I'll try to do my best here. An example would be, here's a low note, and a higher note that sounds the same would be, Hope I didn't do too bad of a job. I hope my music teachers still like me. But those two notes, if you listen to them again, they kind of sound the same. They both might be, for example, the note we call C, but one is at a low octave, one is at a high octave. In your textbook, they show on a table, for example, a note that is called C might have a frequency of 256 hertz, and if you go up the scale, C, D, E, F, G, like that, and you get up to the next C, it's 512. Well, what do you notice about this? The thing that you're going to find out when you read is that to go up an octave, you multiply by 2. And that is essentially what octaves are all about. To go up an octave, multiply by 2. if you want to go up 1 octave, for example. Suppose you want to go up 2 octaves, then multiply by 2, and then multiply by 2 again, or multiply by 2 squared. If you want to go up 3 octaves, I can't possibly sing this to you. I can't sing through a range of 3 octaves. I don't know how many singers can. Times 2 times 2 times 2. That would be times 2 cubed. So double, quadruple, 8 times, right? That's how octaves work. And if you're going down in an octave, if you want to go down, then don't multiply, divide by 2. If you want to go down 2 octaves, then divide by 2 twice, giving you a total of division by 4, right? Pretty simple. And now you might be wondering, however, how do all of these middle frequencies come into play for all the other notes? It's quite complicated, but I'll give you, for those of you who are mathematically inclined, a quick lesson in how this musical note stuff works. If you know your musical notes, you know that you can sing 12 notes as you go up an octave. Here is roughly what they sound like. Again, my apologies, but you'd go C, C sharp, D, D sharp, E, E sharp, F, and you go up that. It's called a chromatic scale. There are actually 12 notes in there. They aren't showing you the semitones or the sharps in there, but there's a total of 12 notes in the doubling of your frequency. So let's do a little bit of math here, which if you don't get this, don't sweat it. But we want to multiply our frequency by 2 in 12 parts. And the way to do this is to take 2 and raise it to the 1/12th power, so that if we do this 12 times, we will end up, oops, just imagine doing this, 2 to the 12 times 2 to the 12 times 2 to the 12 times 2 to the 12, all the way 12 times. Well, everyone knows that if you do 2 to the 1/12th, and you do that 12 times, that is equal to 2. You've doubled. In other words, you've gone from, let's say, 256 hertz to 512 hertz. And that would get you up an octave. So go try this. Multiply 256 by 2 to the 1/12th, and keep doing that on and on and on, and see what numbers you get here. And now remember, you're not going to get each of these, you're going to get some different numbers because they're only showing you the whole notes. They aren't showing you what are called semitones, but you will see calculator numbers pretty close to these if you try that. This is on what's called the scientific scale, which is commonly quoted. There's a whole bunch of musical scales. They're quite complex when you get down to it. Here's another one. This is called the equal tempered scale. You can try it here too, but if you try what I suggested, multiplying by 2 to the 12th repeated times, you're going to see the frequency climb and hit a few of these numbers on your way. What I want you to know is this part. I want you to know this part, that when you double the frequency, you go up an octave, and when you have the frequency, you go down an octave. All right, enough said. Moving on. One thing that we often talk about when we're talking about sounds is how loud they are. And some people also use the term intensity. What is loudness? What is intensity? Are they related? The answer is yes. And we're going to start off by talking about what's called intensity. When we talk about intensity, we're talking about how much power the sound wave has produced. And if you remember from grade 9, power is measured in watts, where 1 watt is equal to 1 joule of energy produced every second. So sound intensity involves delivering energy, remember energy is in joules, to your ear over a period of time. The quicker we can deliver that energy, the more powerful it is. And of course, the more energy we deliver in a certain amount of time, the more power there is. However, if you've ever stood close to a speaker, you know it sounds very loud. And if you've ever stood very far, you know it gets softer. So there's also the idea here that the power spreads out as you move away from a sound source. Sound moves away from, let's say, a speaker quite often in a spherical shape. So if I try to get you to imagine a sphere of noise spreading out around a speaker, so the energy is flowing outward in all directions like that, and you're trying to imagine a bubble of sound expanding, well, all that power is being spread over the surface of this bubble. And of course, the surface, that refers to area. So what we're really talking about when we discuss sound intensity is how much power in watts is being spread over the area, and that, of course, is in square meters. So your book will explain in more detail that when we talk about intensity, we're talking about watts of power per square meter of area that the sound has spread out over. Now, here's some more information once you internalize this concept. There's the idea that there's got to be some minimum amount of intensity that your ear can detect. And believe it or not, for the human hearing, the minimum intensity is a tiny amount. It's actually so small, we have to use scientific notation. It's 1 × 10⁻12 watts per square meter. And since, if you remember with your metric prefixes, 10⁻12 does have a metric prefix. It's the metric prefix pico. So what we're ending up getting here is that the minimum intensity that you can hear is 1, this is pico, so PW, picowatt, per square meter. This is the minimum. I'll circle it in a different color. Now, what they do next to help get us away from these awful units of picowatts per square meter, you got to think of the pico, you got to think of dividing by square meters. What we do is we go into scientific notation. We're going to write this number as follows. The number 1, written in scientific notation, can be written as 1 × 10⁻⁻⁻. You agree? 1 × 10⁻⁻⁻ is equal to 1. So this is how we write the picowatts per square meter. And why do we do that? Because this is the threshold of hearing, the minimum sound that you can hear. Because there's a 0 in here, what we do is we grab that 0 and we go all the way up to this table right here. And this is what I'm sure all of you have heard of called decibel. 0 decibel doesn't mean no sound. It just means the minimum sound that your ear can detect. 1 × 10⁻⁻⁻ picowatt per square meter. Now, deci, the letter D, in metric, again, you have to know your metric prefixes. If you have not memorized them, go right to the back of the book and memorize them now. You have to know these. Deci means a tenth, 0.1. So 0 decibel is actually 0 bell. 10 decibel is 1 bell. 20 decibel is 2 bell, and so on, all the way up to 120 decibel would be 12 bell, and so on. Now, we also know that we can fill in 0 bell with 1 × 10⁻⁻⁻. So what do you think we would do here? Well, 1 bell, which is 10 decibel, would be 1 × 10⁻⁻⁻⁻ picowatts per square meter. 20 decibel, which is 2 bell, would be 1 × 10⁻⁻² picowatts per square meter. 30 decibel is 3 bell, which is 1 × 10⁻³ picowatts per square meter. 120 bell, 120 decibel, 1 × 10⁻12 picowatts per square meter. All right, so if you look through this, you see the relationship between the power, the intensity, the power per square meter that we talked about, and something called the bell number, and then something called the decibel number, which is probably what you're familiar with if you've ever heard of sound intensities measured in decibel. This is an interesting chart. It shows you what kinds of sounds have intensities with the following decibel or bell or picowatt per square meter measurements. And as you can see, once you get up to, like here would be a very loud place to work. If you worked on the subway, the TTC, think of how loud that would be. 8 hours a day of working, 5 days a week for your entire life, 90 decibel intensity, you could get hearing loss from that. And so you'll see the TTC subway workers walking around with earplugs in their ear because they don't want to go deaf or have hearing loss before their time. Of course, some really loud sounds, a pneumatic drill on a pavement with some of those workers, 110 decibel, 11 bell, 1 times 10 to the 11 picowatts per square meter, and then actually painful hearing over here. Let's think about this number for a sec. 1 times 10 to the 12 picowatts is actually equal to 1 watt per square meter, because 10 to the 12 is a trillion, pico is a trillionth. This is actually 1 watt per square meter. If your ear picked up 1 watt of power per square meter of surface area, you would be in pain. That's just 1 watt. That's how sensitive your ears are. Let's move on. When we're hearing sound, it's not just how intense it is, it's also what frequency the sound is at. So for example, maybe you've heard of what's called the audible spectrum of hearing. The audible spectrum refers to the range of frequencies that we can hear. We can't hear every frequency. I'll just write this in. We can't hear every frequency. Maybe you've heard that dogs can hear really high-pitched sounds. That's true. They can hear higher frequencies than we can hear. In fact, looking at what's called the audible spectrum chart, I've borrowed this one from somewhere on a Google search. You see they show where a piano plays along here, where an electronic piano, a synthesizer can play, bass guitar, bass drum, regular guitar, the snare drum, the rasp of a snare drum, human voice, a high-pitched cymbal crash. You see the frequencies here. Very little of our musical instruments produce frequencies in the 10, 20, 30 hertz range. Very low sounding notes, 27, 28, 50, 40 hertz, very low frequencies like a bass guitar, for example, or a bass drum. Getting into the 50s, 100s, 200s, 400s, now we're in the middle of a piano range, which is kind of where the voice is, where a lot of people sing, so human voice. So these are sounds we're comfortable with. And as you get to higher frequencies, there isn't much. People don't sing that high. You rarely play this high on a piano. Cymbal crashes, you don't want to be listening to those all day. They're nice once in a while, but too much of them is kind of annoying. And so what do you notice? When you get up into the high thousands and tens of thousands of hertz, you can't really hear anything. So this is what we call the audible spectrum. It starts maybe around 20 hertz for most people, and it goes as high as about 20,000 hertz, or 20, what would that be in metric? See if you can guess it with a metric prefix. 20 kilohertz. Once again, if you don't know your metric prefixes, you better start learning. You do need to know them off by heart. This is what we call the audible spectrum. This is a graph from your textbook which shows what is the minimum intensity that you need to be able to hear at certain frequencies. So for a human of average hearing, along the green path here, you can see that if the frequency is very low, like 16, 20, 30 hertz, it's got to be very intense, like 90 or 100 decibel, for you to be able to hear it, because we don't hear low frequency notes very well. As we move into the middle of the range, in the 2, 3, 400 hertz range, that's where pianos are played a lot of the time, guitars, human voice for singing. Now, look where the graph is. It's right down around the 20 or 30, not even, sorry, the 20 decibel range. This is telling you that at these frequencies, the sound only has to be about 20 decibel for you to be able to hear it, because our hearing gets more sensitive there. And then when the frequency gets really high, so 8 times 10 to the 3, 8,000 hertz, 16 times 10 to the 3, 16,000 hertz. In this range, you have to have a pretty loud, pretty intense, rather, sound, like 60 decibel, in order to hear it. We don't hear very well at this frequency range. Dogs do. The dog's hearing, which is along the orange path here, right here, unfortunately I've put a line through it, but dogs, they do really well in the higher frequency range. We don't even hear there. Our ears don't respond to it. This higher frequency range is called ultrasound. That would be up here. And down here, below what we can hear, would be called infrasound. And of course, in the region that we can hear is called audible, the audible region of the spectrum. All right? We're almost done what we came to discuss, folks. If you look back here, we talked about producing sound and hearing sound. What's left is the speed of sound, and there really isn't too much to talk to you about here. Well, actually, sorry, I shouldn't say that. There is a lot to talk to you about, but I don't have any graphics for you. It's very hard to show sound moving from one place to another. What the textbook's going to discuss with you is that the speed of sound, v, is around 300 meters per second. In fact, they're going to say it's around 331 meters per second. But then they're going to show you an equation which adds in a little extra piece, which looks like this. It's going to have a little bit extra, 0.59 t, where t is not the time. T is the temperature. Now, why would they say that? Let's think for a moment. Sound travels through air. And of course, air is made up of molecules of oxygen and nitrogen, among other things. And as you know from grade 9, the hotter the air is, or any gas for that matter, the faster the molecules move. Now, you probably might remember, hopefully you remember from early on in the course, that sound travels as a longitudinal wave, and it travels when one molecule bumps into its neighboring molecule and transfers the vibration. Well, you can't travel any faster than how fast those molecules are moving, so actually, the hotter the gas, or the air, the higher the speed of sound. Hence this formula here. So all we do is we take the temperature in degrees Celsius, and we substitute it in here, and we multiply by 0.59. And then we add 331, and this gives us the speed of sound in a certain air temperature. Now, give me a moment here. I just remembered that I have a sample problem that I've set up for you. It's actually one of the sample problems in the textbook, and what I'd like to do is just go through that right now. Let's see if I can find it here. Not that, not that, not that, not that, not that. Oh boy, maybe I don't have it here. If I don't have it here, that would be very bad. Let me take a look. Bear with me, folks. There it is. I knew I had it in there. So here's a question. We've got a question that's dealing with the speed of sound and temperature. It says 2 mountain climbers partway up a mountain clap their hands and they hear echoes returning to them. So let's just picture this. They're climbing up a mountain, so I'll do my best to draw a mountain. Here they go. And I imagine there's other mountains around. They clap their hands and they hear echoes return from the mountain face opposite them. So the sound of their clap goes that way and it comes back to their ears. This is an echo. And they say that it takes 6 seconds, from which I bet you can figure out that that's 3 seconds each way. The air temperature is -5 Celsius, so right away we know that the speed of sound can be calculated, 331 plus 0.59. Be careful here, this is a negative temperature, so -5. And what's that going to do? That's going to bring the speed of sound down just a little bit below 331 by, oh, I don't know, 2 or 3 degrees, right? Make sure you get a number below 331. And what's that going to come to? I get my calculator out here. I should have had this prepared, but it's been a busy day. So here we go, 331 minus 0.59 times -5. There we go. And whoops. You guys probably already have this calculated. I'm struggling with my calculator here. There we go. I get 328.05 meters per second. So let me ask you this. If something took 3 seconds to go each way at a speed of 328.05 meters per second, how far away is that something? Well, folks, this is a job for speed equals distance over time. Solve for distance. by plugging in the speed and by plugging in the time. And that's all I got for you today. There is more. We will discuss it in class. I wanted to keep this as short as possible. I hope I've done that to some extent. Thanks for watching, and I'll see you guys later.